Hi guys, so what we're going to do today is we are going to apply what we did last class to a parent function. And this is a process that we're going to do over and over and over again this year to the point where you are probably going to get sick of it. But that's okay because it's one of the most important things that we're going to do in this class. So the parent function we're going to look at today is absolute value, and that's what we're going to spend the rest of this unit on. So the first thing we'll do is just talk about what absolute value is. Absolute value is the distance of a number from zero. It's denoted by these little straight bars, not parentheses, but just little straight lines. So the absolute value of 3 is just 3, because 3 is 3 away from 0. The absolute value of negative 2 is 2, because that's how far away it is from 0. The absolute value of 0 is 0. And then something like this, you can treat it like parentheses and actually do what's inside of it. And then the absolute value of negative 5 is 5, because again, that's how far away it is from 0. So to see what the absolute value parent function looks like on a graph, we're going to plot some points. But this is the equation. So what a parent function is basically that equation with 0 transformations. Every other absolute value function that you have is some variation of this parent function with transformations applied. So if I take 0 and plug it in, the absolute value of 0 is 0. If I plug in 1, the absolute value of 1 is 1. Plug in 2, the absolute value of 2 is 2. Plug in 3, the absolute value of 3 is 3. You probably see a pattern. Let's do some negatives. The absolute value of negative 1 is 1. The absolute value of negative 2 is 2. The absolute value of negative 3 is 3. So if I plot those points, you'll notice that shapes start to take place. And this one is probably one of the easiest shapes for most people to remember because absolute value looks like a V. So this is the shape of the parent function. Every other absolute value function that we graph is a variation of this graph with transformations. So what we're going to do now is we're going to review all the vocab we did from the very first unit. So domain. Well, domain here is negative infinity to infinity. Nothing has changed. Range. Range, we look bottom to top. The lowest y value here is 0. It actually touches 0, so it gets a bracket. And then it continues to infinity. Increasing intervals. Remember, increasing is left to right. As our x's get bigger, the y's are getting bigger. So the way we'd write that section, that's from 0 to infinity. Decreasing. That's this section of my graph over here. So this graph is decreasing from negative infinity to 0. Extrema, those are, there's a couple of those that we'll talk about later this year. Really what that means, does this graph have an absolute minimum or maximum, or a global minimum or maximum? And this graph does. This graph has an absolute or global minimum at 0, 0. That point is the vertex. End behavior. Remember, we write two statements. As x approaches negative infinity, what's f of x doing? In this case, as x approaches negative infinity, f of x is getting bigger and approaching infinity. Then we write a second statement. As x approaches positive infinity, what's f of x doing? Well, as x approaches positive infinity, f of x is also approaching infinity. And then the last thing is symmetry. So this is something we may have talked about this year so far, probably not so much. This graph has an axis of symmetry on it. Okay, this axis of symmetry happens to be the y-axis. All of these absolute value functions will have an axis of symmetry. You probably heard that term last year when you did quadratics. What's unique about this graph, though, is because the x equals 0 is the axis of symmetry, because it's the y-axis, this is actually something called an even function. And we'll talk more about that a little bit later this year, but that's kind of a unique thing about the absolute value parent function. All right, so what we're going to look at now is really what we looked at last class with transformations. So the first part we're going to fill in, this description, is really the same thing as last class. So if you remember, all of these are horizontal transformations because they're occurring inside the parentheses. So this first one is a shift right. Then we have a shift left. Remember, the horizontal stuff is backwards. That b, it depends on the value of b. If it's greater than 1, it's a horizontal compression. If it's between 0 and 1, it's a horizontal stretch. And then that negative y, that's a reflection over the y-axis. So what I'm going to do now is I'm going to write what this actually looks like when we apply it to the absolute value parent function. So if we actually take f of x equals the absolute value of x, and we actually apply f of x minus h. That means I replace x with x minus h. So what that looks like in the absolute value function is the absolute value of x minus h inside the absolute value bars. Same thing with plus h. Same thing with b. And the same thing with the negative. So all of those horizontal transformations are occurring inside the absolute value bars. So anything that's inside the absolute value bars is going to be a horizontal change. Now, how these actually apply to our function, we'll look at later, but for now, we're just identifying kind of what those transformations are. All right, then again, last class we talked about these transformations. Those were all vertical transformations. So this would be a shift up. This is a shift down. If a is greater than 1, that's a vertical stretch. If a is in between 0 and 1, it's a vertical compression. And this was a reflection over the x-axis. So how this looks actually applied to the parent function. We take the parent function, and then we add k. Take the parent function, subtract k. Multiply it by a, or we make it negative. So all of these vertical changes, you'll notice, occur outside the absolute value bars. So any transformation that's outside the absolute value bars is a vertical transformation. Now, when we have multiple of these transformations, it'll be in some form of this order, okay? One thing you'll notice, inside those absolute value bars, anything in front of that x has been factored out. The reason we do that is because it makes it really obvious what the vertex is. That vertex is hk, and we'll use that here in a little bit. But let's go ahead and look at some examples. Okay, so what we're going to do to graph this, we're going to start by just listing what the transformations are, and then we're going to find the vertex. So transformations on this first one. That -2, that is a shift to the right 2. This -3, that is a shift down 3. Any shifts left, right, up, or down are going to shift the vertex. The vertex is normally at 0, 0, but it has now gone right 2 and down 3, which means your vertex is at 2, negative 3. So like we said, if it's in that form of x minus h plus k, hk is the vertex. And that's probably the most important thing for us to get. All right, now to actually sketch this graph, there's two ways to do it. Now this absolute value is kind of unique in the way we graph it. It has a couple little properties that make it a little bit easier, but I want you guys to see the process that we're going to use for some future graphs. So what we're going to do is we're going to look at how this graph's parent function normally looks. Normally from the parent function, we went over 1 and up 1, over 2 and up 2, over 3 and up 3, et cetera, et cetera, et cetera. That's how we moved from the vertex. Those happen to be points on the graph, but it's also how we moved in relation to the vertex. We're going to do the same thing on this graph, but we're going to do it from the new vertex. So from that vertex, we're going to go right 1 and up 1, right 2 and up 2, right 3 and up 3. And because this graph has an axis of symmetry, we'll do the same thing on the other side. All right, now this graph's domain is negative infinity to infinity, range bottom to top. It actually touches that y value, so it has a bracket, and that's my range. Now, one thing you may notice about this graph, look at the slope coming from this point right here. Up 1 over 1, up 1 over 1, up 1 over 1. Whatever value we end up with here, that's actually going to be the slope coming off the vertex. Now, most of the graphs that we do this year aren't going to work out that way. Actually, none of the graphs we do this year are going to work out that way. Absolute value really has a couple of unique things to it. All right, let's try this next one. Transformations. Negative out in front, that is a reflection over the x-axis. That means that this graph is going to open down. +2, that is a shift up 2. That means my vertex is at 0, 2. Again, normally this graph, from the parent, we would go right 1, up 1, right 2, up 2, right 3, up 3. But what's different this time, first of all, this is going to be from the new vertex, which is 0, 2. But we're not going to go up 1 because it's been reflected. Since it's been reflected, we're going to go down 1, down 2, and down 3. So right 1, down 1, right 2, down 2, right 3, down 3. Again, each time we do that, it's in relation to that vertex point. And we're doing the same thing on the opposite side because of that axis of symmetry. Domain, you're probably going to notice a pattern here. Domain on these is always negative infinity to infinity. Range, bottom to top. We have to go in order, bottom to top, negative infinity to 2 with a bracket. All right, let's try another one. So this graph has a vertical stretch, and this graph has shifted right 1. That means that the vertex is going to be at 1, 0. Now again, typically what we would do from the vertex will follow what the parent function does. The parent function from the vertex, right 1, up 1, right 2, up 2, right 3, up 3. But this time, it's different because it's been stretched by 2. So since it's been stretched by 2, that's going to affect how much we go up. So we're going to go right 1, up 2, right 2, up 4, right 3, up 6. We're multiplying those values by 2 because it's been stretched vertically by a factor of 2. Now again, these are not coordinates. This is how we're moving from the vertex. So from the vertex, right 1, up 2. From the vertex, right 2, up 1, 2, 3, 4. Let me erase those other points. From the vertex, right 3, up 6. And then follow those same points to the other side. Again, what you'll probably notice, this number is the slope of this part of my graph. I'm going up 2 over 1, up 2 over 1, up 2 over 1. So you can also use that to help you draw your graph. Domain, negative infinity to infinity. Range, 0 to infinity. End behavior, 2 statements. As x approaches negative infinity, f of x approaches infinity. And as x approaches positive infinity, f of x approaches positive infinity. All right, let's try the next one. Transformations. Reflection over the x. The 3/4 is a vertical compression. I've gone left 1, and I've gone down 2. If I've gone left 1 and down 2, that means my vertex is at negative 1, negative 2. Now this one, again, kind of following that same idea. Normally, right 1, up 1, right 2, up 2, right 3, up 3, right 4, up 4. I can go ahead and take all those and multiply them by a negative 3/4. Those are going to be kind of ugly points to graph, so I'm really not going to want to graph those. What I'm going to do instead is using what we just noticed on that pattern, this number here is the slope coming off of the vertex point. Because there's a negative in front, it's going to open down. So from the vertex, I'm going to open down, and I'm going to have a slope of negative 3 over 4. So I'm going to go right 3, down 4. And I'm going to do the same thing on the other side because it has an axis of symmetry. So over 3, down 4. Domain has not changed. Range is bottom to top with a bracket. As x approaches negative infinity, this time f of x is approaching negative infinity. And as x approaches positive infinity, f of x is approaching negative infinity as well. So again, the process to kind of graph this here, find the vertex, okay? Opposite sign of this is the x-coordinate. The sign of this is the y-coordinate. From that vertex, if there's a negative, it opens down. If there's a positive, it opens up. Whatever you have out here, that is the slope and what how you're moving from the vertex. Now, what we're going to look at is what's going to happen if we have more kind of on the inside of these absolute value bars. Absolute value has a couple kind of unique properties that makes graphing these a little bit easier and also just a little bit different. Some of those properties, we know that the absolute value of something, it has to be greater than or equal to 0. The absolute value of a negative, really, if anytime it's a negative, it's going to be the same thing as the absolute value of a positive, because the absolute value of a negative is just a positive number. Another unique property that we're going to use here when we graph, if you have multiplication, you can separate that into two different absolute values, and that's what we're going to use on this next one. So what we're going to do here, before I list these transformations, I'm going to start by rewriting this. Now, one thing we talked about, whatever's in front of that x, we want to factor it out. It's still going to be inside the absolute value bars, but I'm going to factor it out for the purpose of making it easier to see the vertex. So the x-coordinate of my vertex is not 2. Okay, the x-coordinate of my vertex, I have to factor this out and rewrite it before I determine what that is. Once I've done that, if you guys, these are the same thing, okay? If I go back and distribute, I get the same thing. But I want it in this form with whatever is in front factored out, because that makes it clear what the x-coordinate of the vertex is. And in this case, it's 1. No shifts up or down, so this is 0. Transformations, that 2 is a horizontal compression. And we've also shifted right. So we'll go ahead and plot our vertex 1, 0. The thing is, though, we don't know what the slope is because there's nothing out here. Well, because of this unique property over here, what we can do is we can actually rewrite this. So using this property, okay, what I have right now, I have the absolute value of 2 times x minus 1. Using that property, I can rewrite that as the absolute value of 2 times the absolute value of x minus 1. Well, the absolute value of 2 is just 2. So this is the same thing as 2 times the absolute value of x minus 1. So that 2 can actually move to the outside. Now, it's really important you guys understand this. This will not work for other functions that we work with. Okay, absolute value is super unique just by the properties that it has and the way the graph looks. We can't just take this 2 and move it out on other functions. But absolute value, it does work out that way. So now when I graph this, I already found the vertex. Now I can see that slope. That slope is 2. So I'm going to go up 2 over 1. It's going to open up because it's positive. And now I have my graph. Domain, negative infinity to infinity. Range, is a bracket, 0 to infinity. All right, so now let's look at another one. Again, whatever is in front of that x, I want to factor it out before I find the vertex. The x-coordinate of the vertex here is not negative 2 because I need to rewrite this with the negative factored out. All right, let's list our transformations. This is a vertical compression. This is a reflection over the y. We've shifted to the right 2, and we've shifted down 1. So my vertex here is positive 2, negative 1. So again, factor out whatever's in front of that x. Now again, what's kind of unique here, that negative isn't going to move to the outside. Any number that's there, yes, that moved to the outside because of this property. But because of this property, that negative doesn't move to the front. That negative actually disappears. Okay, think about the parent function. If you have that parent function and you reflect it over the y-axis, it doesn't change. It's still the same thing. So that negative, the absolute value of a negative, okay, the absolute value of negative 5 is just 5. The absolute value of negative 3 is just 3. It's not negative 3 or negative 5. So that negative doesn't move to the front. That negative actually disappears. So this is actually the same thing as 2/5 x minus 2 minus 1. So now we can draw our graph. From that point, we have a slope of 2/5, so up 2 over 5, which is going to go off my graph a little bit. Domain and range. So two kind of unique properties for some of these absolute value functions. All right, so what we're going to do now is we're going to work backwards. Okay, we're given the graph, we're going to write the equation. So looking at this first one, whenever we write this, it's going to be in this form where it's the absolute value. Well, let me put this. A, absolute value, B, x minus h plus k. Now this b value, you don't have to have, okay? We'll do a couple examples where you do have to write it with that b value, but you're still going to get a correct equation if you don't worry about that b value. And instead, we just use this form. Okay, you will get a correct value here. So we're just going to use this setup. hk is the vertex. Okay, the vertex here is 3, negative 2. So this becomes x minus 3 minus 2. A is the slope coming off that vertex. Up 2 over 1. It opens up, so it's positive. All right, let's look at the next one. So absolute value, this is A, absolute value x minus h plus k. 1, 3 is that point. That's the vertex. So this is x minus 1 plus 3. It's negative slope, so this is a negative, but that slope is 1, so we don't need any number in front. So this is my equation. All right, last one. We're going to write this off of words now, okay? So we're going to take the absolute value parent function. We're going to start in this first one. It says it's shifted right. It's reflected over the x-axis, then followed by a vertical shift. So this graph is actually going to have some order things that we need to pay attention to. So we'll start shifted right. That's f of x plus 3. Reflected over the x-axis, that is a negative out in front. So this will be f of x equals negative absolute value of x plus 3. After we've done those transformations, the next transformation is a shift up. So a shift up 2 is f of x plus 2. So we're going to take that function and add 2. And that's my equation. All right, let's look at the next one. Shifted left 2, up 4. So that's what we're doing first. Left 2, that's f of x plus 2. And you guys, I just realized I just did that last one backwards. That last one says it shifted right. Whoops. That should be a minus. That's minus. Sorry about that, guys. There we go. All right. So f of x plus 2 for shifting left. Shifting up 4, that's going to be a plus 4. So that becomes f of x equals x plus 2 plus 4. All right, now the next one, it says followed by a vertical stretch by a factor of 2. A vertical stretch by a factor of 2 is 2 times f of x. So we're going to take the f of x equation that we have and multiply it by 2. Now be careful here. I can't just stick a 2 out in front, because that's not multiplying the function that I currently have. The function I currently have is that whole thing needs to get multiplied by 2. So if I do 2 times this whole thing, I get 2 absolute value of x plus 2 plus 8. All right, and then looking at this last one. Horizontal compression by a factor of 1/2. Now be careful. 1/2 horizontal compression. What that's going to look like in our equation is f of 2x. All right. Then it says followed by a shift down to 2. So a shift down 2 is going to be f of x minus 2. So this is going to be the absolute value of 2x minus 2. All right, so that is it for absolute value functions. Again, kind of this process that we're going through with identifying the transformations and the vertex. We'll see this again a couple other times throughout this year. So hopefully you get familiar with these transformations because they are going to keep coming back up throughout this year.